physics is fundamentally an experimental science. So even if you start with a theory, you should satisfy some sort of experiment and observation and be tested experimentally to really last this, to really stand the test of time, to be taken seriously over time. But some discoveries are actually made in the lab experimentally. They're more of that experimental nature. So those are, roughly physics has experiment and theory. Those are the two sort of families. And some things are discovered experimentally and some things are first discovered theoretically, and then they're confirmed or not confirmed by experiment, okay? Or sometimes they're constrained by experiment. You can have a theory that sort of predicts something, and then experiments go and try to see if that thing exists. And if it doesn't, or it doesn't to the extent that the theory predicted, then the experiment can actually constrain and put limits on that theory. So that too is actually work that is done constantly in physics. It's something that I worked on myself in particle astrophysics. And so those are sort of the ebbs and flows that go on in physics. Hello, Seaman. Can we get 20 likes? Thank you so much. And can we get a super chat of $500,000 to support the channel, or $500, or $5, or $550? How about that? So those are other options. General relativity describes gravity with such a deep inner elegance. So once again, remember, general theory of relativity was needed to describe gravitation because special theory of relativity did not include gravitation. It did not give us an explanation for acceleration or gravitation. So he had to work on general theory of relativity as a good student of physics that he was, Einstein, because if he didn't, then he would be saying that gravitation is not accounted for by himself, by his theory. So he had to work on a more general theory, which gave us gravitation. But in doing so, he also gave us an extremely elegant, deeper understanding of gravitation, just like he did with special theory of relativity with light. We knew about light, but he gave us a much deeper insight into it with his special theory of relativity. Same thing, we knew about gravitation from Newtonian mechanics, from Newton, from all the giants that he's on the shoulders of whom he's standing on. We knew about gravitation, but he gave us a better, deeper, more elegant theory of gravitation with the general theory of relativity. So we will read about that now. So he describes gravity with such a deep inner elegance, with such simple yet powerful ideas that he found it hard to imagine that nature could pass it by. So it was so beautiful, according to Einstein and others, that indeed people didn't think that it could possibly be wrong. Maybe when something is so beautiful, you just accept it. You're just like, you know what, it has to be this way. Because if it's so beautiful, then it means that nature cannot pass it by. For surely this is the way it should be. General relativity, in Einstein's view, was almost too beautiful to be wrong. Aesthetic judgments do not arbitrate scientific discourse, however. And by the way, this is another reason why Einstein and others did not like quantum mechanics and particle physics, because quantum mechanics was not so elegant. Particle physics is not so elegant. It's sort of a jungle of particles and different effects and things and whatnot. So a lot of these classical physicists who worked, for example, Einstein, who worked on general theory of relativity, just kind of hated how jungle-y particle physics became, or quantum mechanics ended up being. And they did not like the lack of elegance in these other theories. But we've talked about how those are the other side of physics, the other sort of dueling side of physics that we have to acknowledge, because those too are very experimentally successful. We cannot ignore them. But oftentimes this general theory of relativity side and the quantum mechanics side do not agree, which is why we needed a bigger theory, a more general theory, a theory of everything, which superstring theory tends to be a candidate for, but unfortunately it cannot be tested. So that's kind of where we are, okay, in a nutshell. So let's see.